Hi, everybody, and welcome to chapter or section 3 on chapter 12. And what we're going to talk about today is we're going to talk about ways that you can multiply vectors. All right, and the first way to multiply vectors is the dot product. And there are more ways to multiply vectors, and we'll talk about the next one on Monday in the cross product. But the first one that we're going to talk about is the dot product. And the dot product is very useful, and throughout this section, I'm going to show you how useful the dot product is. But just to introduce you to how to do the dot product, I'm just going to basically give you the definition. And what the dot product is, it's just a way to multiply two vectors. And what we're doing is we're just adding the product of the corresponding components of the vectors. So here you see we have two vectors, A and B. And the dot product, we just take the product of the corresponding components, and then we just add them. And so the result is A dot B is equal to A sub 1 times B sub 1 plus A sub 2 times B sub 2 plus A sub 3 times B sub 3. And what we're going to get is not a vector. So when we use the dot product between two vectors, we're not getting another vector. What we're going to be getting is going to be a scalar. And so it's normally called either the scalar product or the inner product. So here's example 1. We're just going to do a dot product between two vectors just to show you, how to do it. It's not something that's very complicated, but again, just to get you some practice on doing the dot product. So we're going to do the dot product between A and B, and we have vector A, which is 3i plus 2j minus k, and we have vector B, which is 4i plus 5k. And so now we're just going to go ahead and multiply. So we're going to multiply corresponding parts. So A dot B is equal to 3 times 4 plus 2 times 0, because there is no J in B, so it would have been 0J, plus, looks like negative 1 times 5. And so we multiply. 3 times 4 gives us 12, plus 0, plus negative 1 times 5, so minus 5. 12 minus 5 gives us 7. And there's the dot product. That's all you have to do. And of course, through this, you can see that the result is just a scalar. Now, there are some properties of the dot product, and I'm going to actually show you the proof of the first one of how, A dot A is just the magnitude or the distance of A squared. And so again, A, B, and C are vectors. Again, there's multiple ways to denote vectors, either, by a solid A, solid B, solid C. So like they're in bold, or again, you could say vector A, vector B, and vector C. All right, now the first one is A dot A, and all that's going to give you is just the magnitude squared. I'm going to show that after I just go over each one of these. The second one is kind of like the commutative property. A dot B is going to be equivalent to B dot A. 3, I can do the dot product A dot the sum of two vectors, or I can go ahead and just do the dot product of both vectors and then add the sum of those. 4, I have a scalar C, and I can multiply C times A and then do the dot product with B. I can do the dot product of A and B and then multiply by C, or I can multiply B by the scalar C and then do the dot product of that with A. And then finally, 5, you see that 0 is bolden right here. Because that 0 is bold right there, that means it's the 0 vector. Now, it doesn't mean just 0, it's the 0 vector. And the 0 vector dot A is going to give us 0. Because it's the 0 vector, we're multiplying every component inside of A by 0. Alright, so now I'm going to show you how to just write out kind of the proof of A. And if you notice, it's bold and A, so they're vectors. So I have the same vector, and I'm doing the dot product with itself. So say A is equal to A sub 1, or is the vector A sub 1, A sub 2, A sub 3. And so the dot product of this is multiplying itself. So A dot A is just going to be A sub 1 times A sub 1 plus A sub 2 times A sub 2 plus A sub 3 times A sub 3. I do not need the little vector there. And the result of this would be A sub 1 squared plus A sub 2 squared plus A sub 3 squared. Now this should hopefully, allow you to remember, okay, looks very similar to something. What does this look like? Well, if I just did the magnitude of A, that's the square root of all our components, the sum of all of our components squared. So A sub 1 squared plus A sub 2 squared plus A sub 3 squared. Now, if I square my magnitude, I'm squaring my square root. And so therefore, that's just going to be A sub 1 squared plus A sub 2 squared plus A sub 3 squared. And the result gives us our dot product of A dot A. All right. So for example 2, what we're going to do is we're going to see, are we able to do the dot product with, the vectors and the scalars that we have. All right, and we want to see if it's true or if it's false. If it's false, we will explain why. So for the first one, for A, is that meaningless or is it meaningful? So if it's meaningless, I'll just put an X beside it. If it's meaningful, I'll put a check, and I'll actually talk through this, and I have to write it out, why it is meaningful, why it is meaningless. So A dot B is going to give us a scalar. And then we want to do a dot product with a vector. You cannot do a dot product of a vector and a scalar. So because, let me change that so you don't get confused, that's an answer. It's because A dot B is a scalar, and then we're trying to do another dot product with it. Again, we only can do dot products between two vectors. So that means that this is meaningless, because A dot B is a scalar and C is a vector, and you cannot do the dot product between a scalar and a vector. All right, for B, is that meaningful or meaningless? A dot B is a scalar, and we're multiplying a scalar times a vector. That's meaningful. All right, because A dot B is a scalar, and I'm not doing a dot product with another vector, I'm just multiplying a vector by a scalar, I'm able to do that. We did that on the first day. So that's meaningful. C, we have the magnitude of A, or the distance of A, which is a scalar, and then we're multiplying that scalar times a dot product of B and C. Because the dot product of B and C is also a scalar, it's like multiplying two scalars. So therefore, that is meaningful. For D, we have a dot product of A and the sum of two vectors. Well, we know that the sum of two vectors is still going to produce a vector. And because the sum of two vectors is a vector, I'm allowed to do the dot product of A and B plus C. So that is meaningful. For E, we have a dot product of A and B. That will give us a scalar. Because that will give us a scalar, I cannot add a scalar to a vector. I can only multiply a scalar to a vector. So therefore, E is meaningless. And then F, I have the magnitude of A, which will be a scalar, and I want to do a dot product with a scalar, so that already tells me that it's going to be meaningless because b plus c is a vector, and I cannot do the dot product between a scalar and a vector, so therefore that's meaningless. Alright, now I'm going to end the video right here. I'm going to show a proof to this, and I'm just going to put it up on Schoology. You don't have to watch the proof video. If you're interested in how we're able to derive this formula, then I encourage you to watch the video. But if you don't care, you know, go ahead and skip to the next page for the videos. But all this is right here. So say we have two vectors, and in between these two vectors we have a angle theta. Well, this just is giving us another way of finding the dot product. So instead of, you know, if we don't actually know what vector A and vector B are, but we know the distances of A and B, or we know the magnitudes of A and B, and we know the angle that's made up in between those two vectors, we're able to find the dot product. All right, and then this is also useful in case we want to find cosine theta, which I'll explain on the next page. But that's it. Again, you don't have to watch the next video that I'm going to post. I'm just going to post a proof to this.